These lectures cover the chi-square test and the F distribution. First, we will go through the goodness of fit. Normally, a chi-square goodness of fit test is a goodness of fit test for a categorical variable. Again, chi-square is a non-parametric testing. Now, goodness of fit is a measure of how well a model fits a set of observations. Now, when goodness of fit is high, the values expected based on the model are close to the observed values. But when goodness of fit is low, the values expected based on the model are far from the observed values. So again, a chi-square goodness of fit test is hypothesis testing. And also it allows us to draw conclusion about the distribution of a population based on a sample. Now, using the chi-square goodness of fit test, we can test whether a goodness of fit is good enough to conclude that population follows the distribution. So again, our main objective is to use the chi-square distribution to test whether a frequency distribution fits a Crane distribution. First, we shall go through the term multinomial experiment. A multinomial experiment is a probability experiment, consists of a fixed number of tries in which there are more than two possible outcomes for each independent try. Again, that's why the term is multi. Multi is many. So more than two again. Now, a binomial, bi means two. So a binomial experiment had only two possible outcomes. Now, the probability for each outcome is fixed, and also each outcome is classified into categories. Again, we shall see example. So here we see a radio station claims that the distribution of a music preferences for a listener in a broadcast region is as follows. So we have classical for 4%, country music for 36%, gospel for 11%, oldies for 2%, pop for 18%, rock for 29%. Now, each outcome is classified into categories, and also the probability for each possible outcome is fixed. So those are the two conditions. Now, a chi-square goodness of fit test normally is used to test whether a frequency distribution fits an expected distribution. Also, the null hypothesis states that the frequency distribution fits the specified distribution. Also, the alternative hypothesis will state that the frequency distribution does not fit the specified distribution. So let's go through an example here. Now, to test our previous data, which we have 6 categories of different types of music, we are going to test it. And now to test the radio station claim, the executive can perform a chi-square goodness of fit test using the following hypothesis. So here we have to state that then that's the claim, the null hypothesis, that the distribution of music preferences in the broadcasting region is 4% classical, 36% country, 11% gospel, 2% oldies, 18% pop, and 29% rock. So again, that's our claim. Now, the alternative hypothesis, as we mentioned in the previous lectures, it always goes against the null hypothesis. So in this case, the alternative hypothesis, HA, we said that the distribution of the music preferences differ from the claim or the expected distribution. Now, for us to calculate the test statistics for chi-square goodness of fit test, first we need to know the observed frequencies. So here we say the observed frequencies and the expected frequencies are used. Now, the observed frequencies, which we represent as O of a category, is the frequency for the category observed in the sample data. Then the expected frequency E of a category is the calculated frequency for the category. And normally the formula will be NP or NPI. So here we say expected frequencies are obtained assuming the specified or hypothesized distribution. So the expected frequency for the ith category is EI equal to NPI. So N always will be the number of tries, and also P is the assumed probability of the ith category. So now let's solve the problem. The same solver we have for the, again, the radio station. We have the classical. This is our, previously we have our cream already, the percentage. Now the sample here we have 500. So we say the marketing executive randomly select 500 radio music listeners from the broadcast region and asks each whether he or she prefers classical, country, gospel, oldies, pop, and rock. Remember, we have a claim already for the percentage for each of these 6 categories of music. Now we are going to test it. So we collect a sample of 500 listeners. Now the results are shown on the right side. Now we are going to find the observed frequencies and also the expected frequency for each type of music. So first we start with the observed frequency. We already know the number of radio music listeners naming a particular type of music. And this is the sample we collected or the survey result. Classical is 8, country 210, gospel 72, oldies 10, pop 75, and rock 125. So now we can find the observed frequency, because this is again what we given to us based on the sample we collected. So again, the type of music is 6 different categories. Remember, this is our percentage of listeners, the cream. We already find the observed frequency, which is the sample we collected. Now we can find the expected frequency. Remember, the expected frequency will be 500, which is the N, times the probability or the percentage. This will be the percentage of each category. So the N is always 500. Then classical is 4%. Country is 36%, so that will be 0.36. 11% will be 0.11. So again, in our previous slides, we saw the formula to find the expected is NP or NI equal to PI. So N again is what we find the number of tries, or it can be in our case, is the sample size. And we collect a sample of 500 for 500 music listeners. So again, we already have the observed frequency, as we said. Now we find the expected frequency, which will be NP. So N always is 500. The classical P is 4%, 0.05. And rock, for example, is 29%, so it will be 500 times 0.29. So after that, we say that for each square goodness of fit test to be used, the following must be true. First, we have to look at the observed frequencies must be obtained by using the random sample. So that's our first condition we should know. Then the second condition, each expected frequency must be greater than or equal to 5. Each expected frequency. So that's the condition we have to look here. Let me go back. So this is our expected frequency. We can see that all the values are at least 5, more than 5. So again, each expected frequency must be greater than or equal to 5. So now, if these conditions are satisfied, then the sampling distribution for the goodness of fit test is approximated by chi-square distribution with k-1 degree of freedom. So K is what? The number of categories. In our case, we have 6 different categories of sounds. So K will give us 6 minus 1 for the degree of freedom. Now, the test statistics formula is the sum of the difference of the observed frequency and expected frequency, again, for each category, all square, divided by the expected frequency. So again, we say that O represent the observed frequency of each category, Also, E, the same thing represents the expected frequency of each category. So now, if we know the degree of freedom and we can find the test statistics, then we're almost done. And here we say the test statistics is always a right tail test. So these are the steps to use the goodness of fit test or chi-square goodness of fit test. We have the steps in words and also in symbols. So as we said earlier, first of all, we have to state this is a hypothesis testing. So we need to state our null and also alternative hypothesis. So we state HO and HA. As we said earlier, HO will be the cream. Always HA will go against HO. Then secondly, we have to specify the level of significance, which is the alpha. Majority of the time, by default, it will be 0.05. But it's possible it can be 0.10 or any. Then next, we need to identify the degree of freedom. Degree of freedom is always K minus 1. K will be the number of categories. Again, K will be the number of categories. Then, if we know the degree of freedom, alpha, then we can determine the critical value. Using, again, the textbook we are using, Appendix P, we have the table for the chi-square critical values. Then next, we are going to determine the rejection region, because after the test statistics value and also critical value, we can determine the rejection region. Then, so we calculate the test statistics. And now we have to make our decision. We say make a decision that we are going to reject or we are going to fail to reject the null hypothesis. So here we say that if the chi-square or the test statistics is in the rejection region, then we reject HO. Otherwise, we fail to reject HO. Now, since we already know the critical value, if we know the test statistics, we can determine, again, the rejection region. And we will see an example soon. So after that, we interpret our decision in the context of the original claim. So we are using the same example. Remember, we have, again, 6 different categories of songs. We also collect a survey or a sample size of 500. And we were able to find the expected value. And we also, based on the sample in each category, we were able to find the observed frequency also. Now here they say we should use alpha equal to 0.01. So the level of significance will be only 1%. So now let's follow the steps to solve the problem. This is the steps to solve again. Or here we say performing a goodness of fit test. Again, the same example. Our claim is we have 6 different categories of songs, and each percentage of, again, so 4% listening to classical, 36 country, and the rock is 29%. As we said, HA always go against HO. So the music preferences will differ from the claim or the expected distribution. Next, we already know the alpha value is given to us to be 0.01. To find the degree of freedom, which is DF, we know the number of categories, which is 6 minus 1. That gives us 5. Then from here, we can use the table to find, again, the critical value. So using the table, again, our textbook, the table is table B. We will get 15.086. And also the alpha value, again, 0.01. So now we can see the rejection area and accepted or no rejection area. But now, in order to know this, we need to find the test statistics. So we have all the 6 categories again. We already found the observed frequency. If you remember, we also found the expected frequency. To find the expected frequency, again, it will be NP. N is always 500, the total sample size. And the P will be the category of the probability values, which is not here. The percentage they gave us for each category of type of music. So that's the values we have here. Now we can find the test statistics. So here, 8 minus 20 all square divided by 20, 210 minus 180 all square divided by, again, 180, 72 minus 55 all square divided by 55, 10 minus 10 all square divided by 10, 75 minus 90 divided by 90, and 125 minus 145 all square divided by 145. That's the formula here. And it's a summation. So we are going to add all together. And when we finish, we get 22.713. Then from here, we know our value 15 is here. And we can see 22.713 is on the right side, which means the test statistics is greater than the critical value. So in this case, we fell on the blue area, which is the reject HO. So our final interpretation will be there's enough evidence to conclude that the distribution of the music preferences differ from the claim distribution. So let's try one more example. So here we have a manufacturer of M&M candies claim that the number of different colored candies in bags of dark chocolate M&Ms is uniformly distributed. Now, to test this claim, you randomly select a bag that contains 500 dark chocolate M&Ms. The results are shown in the table on the next slide. We are going to use the alpha equal to 0.10 or 10% to perform a chi-square goodness of fit test to test the claim or expected distribution. What can you conclude? So let's begin. First, this is what given to us. We have 500 dark chocolate M&M, and this is the category brown, yellow, red, blue, orange, and green, and these values are given to us. So next, we say the claim is that distribution is uniform, so the expected frequency of the colors will be the same. They are equal. Again, distribution is uniform, so expected will be the same. Now, to find each expected frequency, we divide the sample size by the number of colors. So here we get E equal to 500 divided by 6, which gives us 83.3. So now let's do our hypothesis testing. So distribution of different colored candies in bags of dark chocolate M&M is uniform, and that is the claim from the question. Now, distribution of different colored candies in bags of dark chocolate M&M is not uniform. Again, always HA will go against HO. Alpha is given to us to be 0.10. The category of the chocolate, we can go back, is 6. The colors, blue, yellow, red, blue, brown, yellow, red, blue, orange, green, 6. So that's why we have 6 minus 1 for the degree of freedom will be 5. Now we can use the table to find our critical value. If we know degree of freedom and the alpha value, we get 9.236 using table in Appendix B, our course textbook. Then next we can find the test statistics. We know the observed frequency. Expected frequency, since the distribution is uniform, it will be the same value throughout, as we said earlier. So here we can again do the same mathematics we do. Difference of 80 and 83.3 divided by 83.3. And since the values are the same, we are going to divide with the same value throughout. And that gives us 3.016. So that will be our test statistics. Now let's go to the diagram. We can see now 3.016 is on the left side, so it fell on the brown area. So this means we are going to fail to reject HO. When it's in the blue area to the right, or what I would say is that if the critical value is greater than the test statistics, then we are going to accept HO, or say fail to reject HO. Now, when the test statistics value is greater than the critical value, then we are going to reject HO. So that's the interpretation here. There is not enough evidence to dispute the claim that distribution is uniform. So that will be the summary of these lectures. In these lectures, we use 2 examples to solve a problem. And this problem is based on using a chi-square goodness of fit test. And hopefully, again, everything is okay. If you have any question, again, feel free to send an email. Thank you.